Hello everyone, so far we have studied about the single, 2 and 3 rotor system where these rotors are coming on a single shaft and that shaft may be of uniform diameter throughout its length or it may be a stepped shaft. But here in this lecture video we will be studying about the geared system where you will be having two shafts which are lying at different locations and those two shafts are connected by a gear arrangement. That means a pinion and gear will be connecting these two shafts. And here if you're observing, there is a main shaft at which one end you are having the rotor and the other end is carrying the pinion. So pinion is the smallest one in gears which are coming in meshing, and this pinion is coming in mesh with the gear, and this gear is carrying, or it is coming at end of the geared shaft, that is the second shaft. At the end the rotor B is coming. So if you are observing from the side, this will be looking like this. That means from the left side view this will be looking like this. So the main shaft is coming here and this is connected through pinion and gear to the geared shaft. At the end the rotor A and this rotor B are coming. So here if you are observing, suppose the pinion or this main shaft that is connected to rotor A is rotating at some angular velocity omega A, then this will be rotating at some angular velocity omega B. Then you are knowing that the velocity ratio is equal to the angular velocity of the driven, that is omega B divided by omega A. And in a similar way you can define the gear ratio. So I will be calling that gear ratio as GR, which is equal to omega A divided by omega B. So this expression you will be requiring in further discussion of this geared system. So gear ratio GR is equal to omega A divided by omega B, where omega A and omega B are the angular velocity of this main shaft and geared shaft. Here the another properties are given. L1 is the length of the main shaft, which is the carrying the rotor A, and its diameter is dA and its speed is omega A. And the other geared shaft is length is L2, the diameter is dB and its speed is omega B. So for the analysis you will be converting this geared system into an equivalent 2 or 3 rotor system based on this some condition that we will be discussing now. So you can convert this geared system into a 2 rotor or 3 rotor equivalent system, and that conversion is depending upon the inertia property of mass moment of inertia of this gear system, that is this pinion and gear arrangement. If the inertia of this gear elements that is located at this position C is negligible compared to the mass moment of inertia of the other two rotors A and B, then you can neglect these components and then you can form an equivalent 2 rotor system. So by forming 2 rotor system means you will be maintaining this first section, that is the main shaft as such. That means it will be having same diameter dA and length L1, and you will be neglecting this mass moment of inertia if it is small. Then the remaining geared shaft will be coming to form a single shaft, and whose length, that means this part will be having a length of L2 dash compared to L2. So that length will be changing. That means we are finding an equivalent part. And this dB will be changing to dB dash, but here we will be maintaining a single diameter similar to dA. So this dB will be becoming dB dash, but it is equal to dA. L2 will be becoming L2 dash, and that value of L2 dash we have to find. And this mass moment of inertia IB will be becoming some another value IB dash. So by converting this geared system into a 2 rotor system means you have to find the value of this L2 dash and this IB dash, and how you can obtain these values, that is our main discussion. And the another case is you can convert this geared system into a 3 rotor system, and that happens when the mass moment of inertia of these gear elements, that is the pinion and gear, are comparable with respect to the mass moment of inertia of the other rotors A and B. So in such a case you can convert this geared system into a 3 rotor system, and here also the first part will be maintaining as such, where the diameter is dA and the length is L1 and the mass moment of inertia is IA as this one, or similar to this one also. But here the diameter will be kept constant, that means dB will be becoming dB dash, but it is same as dA. But the differences are similar to this case, L2 dash and IB dash is coming. So the same way here also same values will also be happening for this L2 dash and IB dash. Along with that, if there is mass moment of inertia of this pinion and gear arrangement, that is IC, and this IC will be equal to the IC1 of pinion plus this IC2 of gear, that we will be seeing, or that you can understand when we are solving a problem also. So anyway, if the total mass moment of inertia of these gear elements are IC, then you can convert or you can form another rotor which makes it a 3 rotor system at this position. Then this IC will be becoming IC dash. So in 2 rotor system you have to evaluate this L2 dash and IB dash only. But if you are forming a 3 rotor system out of this geared one, then you will have to find L2 dash, IB dash, and along with that you will have to find this IC dash also. So how you can find all these values, that is our next main discussion. Suppose we are forming a 2 rotor system, that means we are neglecting the mass moment of inertia of this gear elements, that is pinion and gear. Then you will be getting this 2 rotor system where these 2 rotors are coming. So this IA is same as such in our original case, and DA and L1 part is also same. So only the change in part is this part. Anyway, this pinion and gear we are neglecting, and this part is replaced by this part in the 2 rotor system. So DB will be becoming DB dash, but it is DA. L2 will be becoming L2 dash, and IB will be becoming IB dash. So these 2 values we have to evaluate. So here this one is this main shaft is rotating in an angular velocity of omega A, and this will be rotating in an angular velocity of omega B in such a way that the gear ratio GR is equal to omega A divided by omega B. But here the entire shaft will be rotating at a single angular velocity, that is omega A. You will be applying some conditions between these 2 systems that you are seeing on the left and right. Then you can equate the kinetic energy as well as the potential or strain energy between these systems. So first we will be going for the kinetic energy equivalency between these 2 systems. So for these 2 systems, the first part is similar. That means DA L1 length having mass moment of inertia IA is coming up to this much part also. So equivalency comes in the case of the second part. That means here the DB diameter L2 length IB mass moment of inertia is becoming this much part in the 2 rotor system. That is the DB dash, that is equal to diameter DA, L2 dash and IB. So you can equate the kinetic energy of these 2 systems. So kinetic energy is actually the rotational kinetic energy, which is of the form of half I omega square. So if you are observing this case here, the kinetic energy is which is equal to half into I B into omega B square. And for this part, so this second part we are focusing, the first section is common in both system, and this will be equal to half into IB dash into omega B dash square. But if you are observing, this omega B dash means there is a single frequency in this case, that is there is only omega A. So this omega B dash you can write it as omega A square. So then you can write, or this half and half will be getting cancelled. Here you have to evaluate the change in mass moment of inertia of B, that is IB dash you have to find. So IB dash you can keep on one side, and then this will be becoming IB into omega B divided by omega A the whole square. So this IB dash will be becoming IB into, you are knowing that omega A by omega B is gear ratio, then this can be written as IB divided by the square of gear ratio, that is GR square. So this will be the change in mass moment of inertia if you are forming a 2 rotor system out of this geared system. Then the new mass moment of inertia of the second rotor, which is coming in at the end of this geared shaft, that is IB, will be becoming IB dash, which is equal to IB divided by GR square. So we have evaluated this change in mass moment of inertia of this rotor, and next you have to evaluate this change in length, that is how L2 is changing to L2 dash, or what is the relative connection between this L2 dash and L2. For that, you will be equating the potential energy of these 2 systems. So whenever we are saying system, in both systems, the first part is same, that is the DA diameter and L1 length part is same. Then you will be equating the potential energy or the strain energy of this part in this system, in the geared system, to the second part in the equivalent 2 rotor system. So potential energy or strain energy means in springs you are having the form of half kx square, where k is the stiffness and x is the displacement. But here you are having the rotating system or rotor system, so where the k will be replaced by q, which is the torsional stiffness, and x will be replaced by the angular displacement theta. So you can write it as half q theta square, and this q is also of the form of gj divided by l. So you can write half into Gj divided by L for the first part, that is the geared system. So this will be becoming G into JB divided by L. Here it is L2, into the theta which is occurring for the part theta b square, and this will be equal to half into g into the second part is actually j b dash divided by L b dash or L2 dash. Here we are finding the L2 dash and into theta b dash square. So here actually you can connect this theta b with respect to omega, because the rate of change of those with respect to time will be giving you the angular velocity. So you can connect, or you can replace this omega b as theta b as omega b square, and this theta b dash will be actually, there will be only the omega a term. So this one you can call it as omega a square. So this half and half will be getting cancelled, and g property, if the shaft material is same, then that will also be same. And now the remaining terms will be only jb divided by L2 into omega b square. This is equal to jb dash divided by L2 dash into omega a square. This omega b dash is actually omega a square. And you are knowing that this j is actually the pi d raised to 4 by 32. So j is directly proportional to this, j is proportional to the diameter raised to 4. So this jb will be becoming db raised to 4 divided by L2 into omega b square is equal to jb dash will be becoming db dash, but it is same in this system, it is db dash is equal to da. So you can write it as dA raised to 4 divided by L2 dash into omega a square. So here you have to evaluate this L2 dash. So you can rearrange or rewrite for L2 dash on left side. Then the remaining terms will be becoming L2 into dA divided by dB the whole raised to 4 into omega a divided by omega b the whole square you will be getting. So this omega by omega b, you can call it as gear ratio. Then finally this L2 dash, I can write L2 dash is equal to L2 into gr square into dA divided by dB the whole raised to 4. So this is the change in length from this L2 to L2 dash. It is equal to L2 into gr square into dA divided by dB the whole raised to 4. So if you are observing, or if you are looking for the change in length from the geared system, in geared system you are having these two lengths L1 and L2. So this is, whenever it is becoming this two rotor system, then the total length will be becoming L1 plus this L2 dash, where L2 dash is actually this L2 into gr square into dA divided by dB the whole raised to 4. So this one you can solve for geared system problem, the torsional vibrations of geared system, where you are converting it into an equivalent two rotor system. So it is based on the assumption that the mass moment of inertia of this gear elements, that is the pinion and gear, are negligible. So if you are considering the mass moment of inertia of this pinion and gear, then this will be becoming a three rotor system, where the only difference or only change is, along with this corrections in L2 dash and IB dash, there will be another term IC dash, that is corresponding to the mass moment of inertia of this gear elements to form a third rotor. So if you are forming a three rotor system from this geared system, as discussed before, the L2 dash will be becoming same, gr square into L2 into dA by dB the whole raised to 4, and this change in mass moment of inertia of the rotor IB dash will be becoming IB divided by the gear ratio gr square. Gr is equal to omega a by omega b, that you are knowing. And here the only difference is IC dash will be becoming, here mass moment of inertia of this pinion and gear we are considering. So if the mass moment of inertia of pinion is this much, that is ICA, and the mass moment of inertia of the gear you are calling it as ICB, then the equivalent mass moment of inertia of the rotor, that is corresponding to the geared elements, will be IC dash, and that you can evaluate using this expression ICA plus ICB divided by gr square. So this is to be used when you are converting the geared system into a three rotor system. So here L2 dash, IB dash and IC dash is coming, but DB dash is same as DA diameter, so that you are using a same diameter throughout the entire length within the three rotor system. So these are the equations which are required for analyzing the geared system by converting it into an equivalent two or three rotor system. And this is somewhat tricky. You will have to concentrate more for this analysis. So a problems from this topic will be discussed in the next lecture video. So hope you understood and thanks for watching.